in this video, we're gonna solve this question here. We have this equation and we want to solve it. In this equation, we notice that we have ln, which is log base e, and log base x. Typically speaking, if we see a variable in the base, that's not good. Okay, that's not good, right? So we should do change of base. Okay, change of base. Okay, the next thing that we should do is actually, we realize that if we have a power here, okay, if we have a power here, most likely it will be good if we substitute. Okay, so whenever we see powers in a logarithmic equation, okay, it will be good if we do a substitution. Sometimes the equation can be simple enough to, for you to skip the substitution. In that case, then you can choose not to do it. But in this case, I think it's best if we just do a substitution. It will make things a little bit easier to deal with. Okay, so let's do the change of base first. Now, before that, let me just copy out the equation. So equals to 3. Okay, so we get this equation here. Let's do change of base. So whenever we do change of base, I usually just duplicate. So on paper, you have to copy it out. What I'm gonna do is I'm gonna erase this denominator. I draw a big bracket, and I'm just gonna say that this becomes a fraction. This fraction will have this base x is a little bit lower than the e, so I'm gonna write x below. The e looks a little bit higher because it's not a subscript, so I'm gonna write it above. Now I can choose log base anything, so I can choose any base I want. In this case, I'm gonna choose ln, okay, log base e. So ln. And the good thing is that ln e is actually just 1. It's like saying log base e and e. So let's recall here that if we have log base, let's say square, okay, let's just say anything, okay, and then we have the same thing out in the logarithm, right? So the base and the argument are the same. This is equals to 1. And a special case is that if I have ln e, this is equals to 1. That's because ln is actually just log base e. So it's like log base e equals to 1. Like this. Okay? It's just that we don't write log base e. Okay? So yeah, so just take note that it technically means that. Okay, which means log base e, ln e is equals to 1. And then my ln x will just go upstairs. Right? So let me just write down the equation again. I have ln x squared plus 2 ln x equals to 3, but I'm going to minus over and equals to 0. From here, what I'm going to do is I will let y equals to ln x. And when I let it equals to ln x, I can substitute it inside the equation. I will get this simple quadratic equation to solve. This quadratic expression can be factorized quite easily. So I'm just going to do that here. So it's plus and then minus 1. Okay. In this case, this will mean that y equals to negative 3 or y equals to positive 1. Usually, we have to reject one of them. Okay, not usually. Actually, in this case, we don't need to reject. Sorry, what I mean was, usually we need to check whether we need to reject one of them. Okay, so we should spend some time to take a look at it. But before we do that, let's bring it back to ln x. So if I do ln x, okay, because y equals to ln x, so I'm just going to put it back. So ln x equals to negative 3 or positive 1. Let's see if these are, is there any issue with this? So how do I remove the ln? How do I get the x out? Ln is just log base e, which means to remove the ln, I exponentiate both sides. exponentiate both sides. Okay, so when I exponentiate both sides, this is like e to the power of log base e, which will cancel out. I'll get back the x. I'll take out the x. So x equals to e to the power of negative 3. Doesn't seem like there's anything wrong. E to the power of negative 3 is just a number. Doesn't really matter. Nothing goes wrong with nothing should go wrong with this. Okay. The next one, the other side will just be x equals to e to the power of 1, or e. Nothing wrong with this either, it's just a number. So we don't have to reject any of the answers. Okay, so we are done with this question. Not too bad. Let's look at the next part. So next part, we are given an equation here, and we want to express P in terms of Q. Usually when they say express P in terms of Q, what you can think of is that Q is kind of like a number. We just want to solve for P. That's about it. Okay, so let's copy this out first. Log P. This is all log base 10 because log base 10 is just LG. Or we denote it as such. Okay, we have this equation here. I want to take out the P's and the Q's. I don't want the log, right? So whenever I have log minus log, okay, we recall. Okay, so I'll write it at the side. Recall, okay, that log base anything A minus log base anything B. This is log base same thing, okay, first guy over second guy, right? So I'm going to do this to the left hand side. I will have P over 2Q. This will be equals to log P plus 2Q. Okay, once I get to this step, I have log something, right? And LG is actually base 10. So I'm going to exponentiate it with 10. So 10 to the power of both sides. What is going to happen is 10 and the log base 10 will cancel out. I'll be able to take out the stuff inside the logarithm. So this will be P over 2Q equals to P plus 2Q. I want to express P in terms of Q. So what I'm going to do is I'm going to just multiply by this 2Q on both sides. I'll get P equals to 2PQ plus 2Q squared, so 4Q squared. I'm going to bring all the P's to one side. Okay, so this will be P minus 2PQ equals to 4Q squared. Factorize out the P. So I'll get this. Okay, and then I will divide the 1 minus 2Q to get P. And I'm done. Okay, so nothing too difficult here. It's just that we can't solve for anything. We're pretending like Q is a number and we solve for P. But nothing too difficult here. Now part 2. State the range of values of P and explain clearly why Q has that range of values. So typically speaking, when we get something like a range of values, we want to talk about what is allowed, what is not allowed. We usually look at the original expression we're given, right? So we are given these few things: 1 term, 2 terms, 3 terms. Okay, and the main thing to remember here, okay, whenever we think of range of values when it comes to logarithms, so we just recall that the argument of a logarithmic function, okay, logarithmic function must be positive. Okay, what this basically means is if I have log base anything and I have a, right, something like that, this means that a must be more than 0. Okay, actually, if this is defined, then a must be more than 0. Or If a is more than 0, then this logarithm term is defined. Okay, so in this case, state the range of values of p. So we just write down that in order for, okay, which term do we need to look at? The simplest one is log p, right? So if log p is defined, that means if it's legal to write it down, right? So in order for log p to be defined, okay, in order for it to be defined, p must be more than 0. So that's the range of values of p. Okay, we are done with that. So this is actually the first step in this question. The next step, we want to explain clearly why q has that range of values. And what we know is that p is more than 0. Second thing is we know that p is equal to this fraction here, right? P is equals to 4q squared over 1 minus 2q. And this whole thing is more than 0, okay, as we've just showed. In this case, for a fraction to be positive, it's either both the numerator and denominator are positive, or both are negative, then they kind of cancel out, and in total is positive. So let's take a look. The numerator is 4q squared, okay? So because we have 4q squared, and 4q squared is positive for all q in real numbers, right? That means any real number q, 4q squared is positive, right? Sorry, not positive, more than equals to 0. Okay, yeah, okay, technically, yeah, okay, yeah, technically this line is true. It's just that because p is more than 0, then this can't really be 0. You know what? Let's just, yeah, actually it's more than 0. Okay, I'll just write it like this. Okay, so it's more than 0 for any q in R, and let's just write down here that q is also more than 0. Okay, and this is since log, let's see, log 2q, okay, log 2q is defined. 2q, oops, 2q is defined. Okay, yeah. Okay, so because the numerator is positive, that means the denominator should also be positive. Okay, so let's write down this. Okay, write down n. Okay, we require that the denominator 1 minus 2q to be positive. Okay, in order for this to be positive, if you solve this inequality here, you will get q is less than half. Okay, so you do shift some stuff around, you will get this inequality. Okay, now I have half of the inequality I want to show. The other half is that q is more than 0. And actually we have written it down already. Let's just say that, okay, let's just write it down again. I think it will be good if we just rearrange this a little bit. Let's write this actually as step 3. And then step 2, I'm going to say that since, okay, let's use a symbol. Since log 2q is defined, okay, 2q must be positive, right? Which also means that q must be positive. So we have this, we have this. So the very last step would be to just combine the two. Okay, so from 1 and 2, equations 1 and 2, okay, from equations 1 and 2, we have that q is between 0 and half. And we are done. Okay, it's not really a show question. They just want us to explain. So we need to be very clear about why each part of the inequality holds. Okay, so let's go on to the next the last part of this question. You don't really need to read this. Basically, it's just they collect some data. We have something that looks like this. I have this scatter plot, right? I have some points on a Cartesian plane. Now they're asking you which of these two equations below should would be the better equation to describe this relationship between the points. So what kind of graph does it look like? That's basically what they're asking. So let's recap a little bit about our exponential and logarithmic graphs. So exponential function usually looks like this, right? When I say usually, I just mean like that's the rough shape you should think of when you think of exponential. And then logarithm should be like this. You can always transform the graphs so that they look slightly different, but the general shape should look like this. Okay, so let's describe in words what each of these mean. For exponential curves, basically, if you use words to describe, you can say that as x increases, okay, y also increases. Yes, they are both, in fact, they are both increasing functions. Like when you read from left to right, the curve is going upwards. They're just going upwards in different ways. In this case, for exponential curves, the rate of increase of y, that means how fast y is increasing, right? Y is increasing, yes. We know in both graphs, the y value is always increasing. But for the exponential curve, as you increase x, y increase faster and faster and faster. So the rate of increase of y is increasing, okay? Or increases, okay? Increases. Now for logarithmic function, okay, slightly different. So we say that when x, or as x increases, the rate of increase of y, okay, y is still increasing, right? The curve is still going upwards, but the rate of increase decreases, right? Because it's getting slower and slower. Instead of going up faster and faster, it goes up slower and slower and slower and slower and slower. So we get these two descriptions. Now, it can be quite clear from just the sketches that this should be a logarithmic function that describes the relationship. But we need to write out in words. So let's just say that the suitable model, okay, would be B. So let's just copy out B, which is y equals to a ln x plus b, okay, is more suitable, okay, since the rate of increase of y, okay, decreases as x increases. Okay, so what we are basically saying is that in this set of data here, right, these points here, as x increases, okay, y is going up, but it's going up slower and slower and slower, right? Slower and slower and slower. So we're just saying that B is more suitable because when we describe these two functions in words, this logarithmic function one agrees a little bit more with our data, right? Our data looks like this, and that's all you need to say. Okay, so you need to pick the correct graph, okay, or sorry, the correct function to describe your relationship. And the second thing is just to say that we just describe in words why a certain function is more suitable. In this case, it's because of the shape, and we just want to use, you know, nice words to describe the shapes. That's basically it. Okay, and that's all for this video.